Welcome back. So, in today's video lecture, we will look at the demonstration of particle size analyzer using master size instrument called master sizer. Okay. Uh, so, this works based on the principles of laser diffraction, right? So, usually, master sizer can be used to measure the or to obtain the particle size distribution, okay, ranging from 10 nanometer to up to few thousands of micron meters, right? So you can measure perform the particle size distribution analysis, both using the wet samples as well as the dry samples. Okay, the theoretical aspects of the particle size analyzer will be covered first, and then the demonstration of the same will be done by one of my students from our research group. Okay. First, let us look at the working principles of the particle size analyzer. Then we will move on to the demonstration part. Okay, let's begin. So I will try to give you some overview of the light scattering and you know and how it works, right? So uh, so little bit of a theory behind the master sizer we'll look up in this. So we all know what is light scattering. So let's say you shine a light, okay? How a matter interacts with the light. Uh, so it depends on several factors. Okay, so particle size is very important, one of the important factors, and we have wavelength of the light. Okay, so that relates the that tells us what is the wavelength at which light was shined, and refractive index. So that tells us how light is diffracting. So once it is interacting with the matter. Okay, so these are some uh, important parameters that you will often see in any light scattering equation, right? So in general, when you shine a light through source, okay, light source, the light which comes from the source uh, interferes with the matter when you are shining the light to the sample, and then we collect certain information after they pass through the sample, and we extract the information, we decode the information from the uh, the raw data that we collect from the analysis, and then we tells so we can find out various parameters like size, molecular weight, surface charge, uh, maybe but all these can be found from the light scattering techniques. Okay, be it master sizer, be it dynamic light scattering, or be it zeta sizer, electrophoretic light scattering, and all that. Now, in general, if you look at, let's say when a light wave is propagating in the x direction, you will collect the electric field on the y-axis, and magnetic field on the z-axis. Okay, so when electric field wave is propagating along the x-axis, you can see that the electric field vector oscillates along the y-axis, and magnetic field vector oscillates along the z-axis. So this is a typical characteristics of electromagnetic wavelength that we all know. So generally visible part of spectrum is associated with the light scattering phenomena, but we know that the light scattering in general we are only considering the electric field part. Okay, we are this magnetic field is not uh, need not be related uh, for this scattering application. Okay, so you can describe this phenomena, whatever we just whatever we just looked at in terms of mathematical, language, that is this one. So E is nothing but E naught. So this, uh, whatever we described physically, can also be described mathematically in this way. So, in a nutshell, if you want to understand the interaction of light, okay, it interacts with the matter in two ways. One is absorption. In this route, the photons disappear, right? So we have nothing to collect. So it is very difficult to um, decode anything from that output. The other one is scattering. Here, photons change the direction, sometime amplitude. Uh, so, so this is what is readily used, okay, for the light scattering technique, because you can at least collect some information and extract some useful information to find something like size of the particle, polymer, or biological sample, molecular weight, and surface charge, right? All these parameters can be determined. Okay. So here, scattering by the particles. So we know that how the scattering works is if you have a sample containing the suspension of particles. So the smaller the part, so the smaller particles uh, reflect or fluctuate more, right? Smaller particles will fluctuate more, so there will be the scattering will be more in that case, right? Whereas larger particles diffuse slowly, so they will so then the scattering that is coming out of the larger particle will be less intense than the scattering coming out of the smaller particles. Okay, so this difference help us uh, to identify the distribution of the particles, right? Basically, we can collect uh, information and put in the right spectrum so that you get the distribution of the particles. Okay, so whenever the intensity of the light beam is weakened by so whenever the light, I mean the matter interacts with the light, it is either weakened or absorbed. Okay, right? So that is what exactly we collect out of it. So whether it is transmitted intensity, okay, in both the cases, okay, how they will disappear. So they will actually there will be exponential decay, and that will be as a function of size of the object or matter that is interacting with the light. So intensity of light is um, you know exponentially, so it depends on the exponential decay, right, of based on the size of the object, okay, and turbidity. So you know that Rayleigh law is proportional to sixth power of size and fourth inversely proportional to fourth power of wavelength. But for my scattering, this is quite complex equation. But in terms of size of the particle, there will be wavelength and there will be refractive index. Okay, it's not as compact as the Rayleigh equation. Okay, but here, if you want to understand how the intensity as a function of size varying, it is the similar equation, but here you will have the scattering vector, that is q. You can also call it as extinction efficiency, which is also function of size, the refractive index, uh, and it I mean this part, and it will also contain information about the concentration of the particles, right, the scattering particles. Okay, so in this way you can calculate intensity as a function of scattering vector. Okay, that will tell us what is the size of the particles eventually. here we are talking about the scattering by the particle master sizer. This master sizer has got two modules, aero and hydro. So which sample is usually done in this hydro mode, and dry powder is done using aero mode. Okay, and it uses principle of laser. Why we use laser diffraction is because it is a convenient source for us to get narrow, uh, you know, spectrum, right? Narrow spectrum, or we can say that it produces light of a single wavelength. If you use white light or visible light, you have multiple wavelengths. So at different point, multiple wavelength will interfere with matter. So it is very difficult to analyze the samples. That's why usually we employ laser for this diffraction application. So it provides accurate and reliable measurements. You can also do analysis for various samples like powder, suspension, emulsion, and aerosols and things like that. I have actually listed some of the advantages, limitations over here. So the basically the applicable range, okay, under this master sizer is between zero point 0.1 micron or 100 nanometer to 1 mm, 1000 micrometer. Okay, so this we should know. Yeah, I think applications I have listed over here. This is so very interesting. Uh, Very interestingly, you can see that these are applied in various fields. Okay, so now you will move on to the demonstration part. It will be done by one of my students. Okay.
Welcome everyone. Today we will be demonstrating the Mastersizer 300, which is a particle size analyzer. Here we will measuring the size of the particles by tracking their scattering pattern when they pass through a laser light using the e-scattering principle. We will be calculating the hydraulic diameter of the particles. So it has two modes. One is the aero mode and another one is the hydro mode. This is the aero mode and this is the hydro mode we have. So based on what kind of dispersion you are using, we will choose which one to actually use. If you are using any kind of liquid, most predominantly water, to disperse the particle, we choose the hydro module. If we are using air to disperse the particles, we will use the aero module. So for today's demonstration, we will be using the hydro module. This we have. The principle is the same, but only the dispersion type is different. So this is the software Mastersizer 3000 associated with the instrument. Just open it by double clicking. At first, we will start with creating a new measurement file. We just have to click here. There you can see that a new measurement file has opened. Next, we go to manual measurements. Here, this is the setting tab. So here you will be inputting all the details of the test that you are going to do. So for demonstration purposes, I have just written the sample name as test. Next, go to particle type. Here you can find all type of particles that are compatible with the analysis. Based on the particle type you have, choose it from here. It could be non-spherical, spherical, or opaque particles. For today's demonstration, I will be using the non-spherical. Next is the material. You, from material, you can find it from the database, or you can feed the data, or or you can need to input the refractive index and absorption index of your material. Uh, Next is dispersion. Again, you can write the value of the refractive index on your own. If the dispersant is any non-conventional fluid, or you can take it from the database. Just skip the instruction part. Next is the measurement. Here, the duration of each step is fed to the instrument. The background measurement time duration and sample measurement duration are both set to uh, 10 seconds each. The background stability time for this demonstration is set to 60 seconds. Next is the sequence. where you let the machine know the number of measurement you are willing to do. You can do 5 or 10 or whatever you desire. So next is the obscuration limit. This is based on how concentrated your sample is. In most cases, obscuration limit should be between 5 to 20%. Now we will skip the alarm part. Next is the accessory that is associated with the instrument. We will start the stir speed. For stabilization purposes, it is recommended that the stirring speed in the beginning is set to 2000 rpm. Next is ultrasonics. If you have particles that are like flocks or aggregates that need to disaggregate to get a proper size of the individual particles, then you could use the ultrasonic as well. You can also control the intensity of the ultrasonication through this step. We will not be using ultrasonics in this case, only the stir speed. Next is the cleaning. This is based on how viscous your dispersant is. Sometimes extensive cleaning is required if you are not using water or any other kind of viscous liquid for the analysis. For this current demonstration, we will choose normal. Next is the analysis part. In most cases, general purposes suffices. Narrow modes and verifications can be chosen based on the application. The particle size analyzer master sizer has a range between 0.005 micron to 5000 microns, but you can leave the size range as it is or based on your applications. Based on your application, for the result type, you could choose between volume distribution, size area distribution, and number distribution, but volume distribution is recommended and selected by defaults. The next section is not very relevant, so we will skip that. After all the settings are input, you will come up with this additional tab where it will ask you to analyze this instrument. Just click this button and it will start initializing. So it may take some time. The background stability timeout was selected as 60 seconds. So it will try to stabilize the background for at least 60 seconds to check. It is measuring the background now. S- uh, Sometimes this measurement of the background takes a bit more time if the instrument is not clean properly. So this time it was clean properly, so it did not take more than 10 seconds. However, sometimes it takes more than 10 or even 30 seconds. So after all this, once the measure sample section turns blue, this means that the system is now ready to measure the sample. At first, we take a 500 ml beaker and fill it to the up to the 400 ml mark, and then we will drop this module over here. And for today's demonstration, we have prepared a silica sample. So this is the silica dispersed in 50 ml of water. So this is the silica suspension that I have prepared for the analysis. So just in case the particles may have settled uh, at the bottom of the beaker, just before putting this into the model, stir it gently. So we are initially putting some amount in it. So and we will have to make sure that the obscuration level is appropriate. So make sure the obscuration level stays between 5% to 20% or whatever values we have fed to the instrument. So we will pour a bit more to increase the obscuration value slightly. It is increasing. See, after it crosses 5%, it turns green. So that indicates that the instrument is now ready for the measurement. Sometimes during measurement, the obscuration value might decrease slightly. To be on the safe side, we will add a few more drops to bring the obscuration value to at least 7% to 8%. Right now, it is around 8 to 10%. The measurement of the sample has now started. It will take 5 measurements or as measurement as you have selected. Though the first measurement values are recorded here. The top one is the D90 value, the middle one is D50, and the bottom one is D10 value. So currently the D50 value, which is the median particle size value, is around 23 microns. So all 5 measurements are now completed. The final value on the graph represents the average of these 5 measurements. So the average value of D50 is 22.6 micrometers, and the D90 is 59.3 micrometers, and D10 is 5.83 micrometers. On the top right of the screen, you can you could see the size distribution. We will now return to the home page. Here, all the values collected from the measurements are recorded. To check and export the result, we will select the average value. Uh, mm, just left click on that, go to the reports, go to trends, uh, select result overlay. Here is the size distribution along with the D10, D50, and D90 values. Sometimes you may need to select multiple measurements to calculate errors, standard deviations, and other parameters like the shorter mean diameter D32. Here we are selecting the 5 measurements files. Go to the report. In the analysis tab, we'll see D32 is 8.39 micron, D43 is 27.9 microns, and D10 is 5.55 microns. D50 is 22.2 microns, and D90 is 57.8 microns. Now export the data. Select the average values here. You can go to the result overlay and copy it as a raw data or as an image as well. The, the raw data will be provided in a text file, or which you can also paste into an Excel sheet as well. So just paste it here and you will see the size values along with the corresponding volume density values. You can also export the data as well in data and D50 and D90 values and the graph as well.